Good evening to all. My name is Ioannis Spanopoulos, and I'm assistant professor at the Department of Chemistry and Chemical Biological Materials Engineering at the University of South Florida. The Spanopoulos group works on the development of next-generation multifunctional materials, addressing limitations pertaining to the development of the materials of the future. So I would like to thank the organizing committee for giving me the opportunity to present our work here in this conference. So the title of my talk is The Emergence of Porous and Water-Stable Metal Halide Semiconductors. Semiconductors is a class of materials that is utilized in a plethora of everyday applications for both domestic and industrial applications, such as solar cells, LEDs, assembly of transistors, capacitors, and all of them, of course, as you can imagine, it's absolutely essential for the advancement of not only for our well-being, but also for the advancements of technology. When the researchers managed to generate porosity to fully inorganic semiconductors, such as silicon, gallium arsenide, germanium, and indium phosphide, then the corresponding materials were able to be utilized in applications going beyond traditional applications for fully inorganic semiconductors, opening new ways and becoming more efficient in applications such as photocatalysis, integrated waveguides, and photonic crystals. One very famous family of hybrid semiconductors is the halide perovskite materials. These materials were named after the natural occurring mineral perovskite or calcium titanate and were discovered in the Ural Mountains in Russia and were named after the Russian mineralogist Count Lev Alexeyevich von Perovskite. The general formula is ABX3, where A and B are cations of suitable size and X are anions again of suitable size. I mention sizes because in order to acquire the cubic aristotype structure of strontium titanate, there are some size limitations that must be fulfilled. The structure consists of BX6 octahedra that span to the three directions, whereas in the formed cubotetrahedral cavities, alpha side cations reside, charge balancing the structure. If the alpha side cation is replaced with bulky organic countercations, then a whole new family of hybrid halide perovskites emerges, each one with unique optoelectronic and mechanical features. This is an example of the 3D fluoramidinium lead iodide perovskite, where fluoramidinium is the countercation that resides in the cubotetrahedral cavities. This is the family of the 3D defective MABI-based perovskites, 1D, 2D corrugated type perovskites, and 2D Russian copper type perovskites. As you can imagine, this structural versatility allows us not only to tune the dimensionality, but also to fine-tune the composition, the mechanical, and the optoelectronic properties of the corresponding materials. These compounds exhibit a combination of features that altogether cannot be found to any other class of semiconductors. These include their solution processability, long carry lifetimes and diffusion lengths, composition of earth-abundant elements, and strong light absorption coefficients. As you can imagine, generation of porosity in this class of hybrid semiconductors would allow them to be utilized in applications going beyond photovoltaics and LEDs, such as photocatalysis, sensing, integrated waveguides, and solid-state batteries. So in order to, so how can this be achieved then? How can generate porous metal halide semiconductors? There is a recent, a very big family of metal halide materials, the so-called open framework metal halide materials, where in this case, the utilization of specific organic countercations bulky enough, bulkier than methylammonium and fluoridinium, can give rise to specific framework architectures with cavities, channels, and different types of pores. Although these compounds, they look porous, in reality, the organic countercations, the templates practically that give rise to these beautiful 3D architectures, reside into the cavities of the material and cannot be removed without structural collapse, because they work not only as a templating agent, but also as a countercation. And all these different types of compounds, despite their beautiful 3D porous network, due to the presence of these organic countercations, there is no accessibility in this porous network. Gas sorption studies are absent, deriving exactly for this limited access to the pore network. So then, how it's possible to achieve porosity in general? In the case of the porous inorganic semiconductors, like porous silicon and porous germanium, there are different types of methods that can be utilized. One of them is the templating methods, using a soft or hard template method, or electrochemical dissolution methods. In the first case, in the case of short and hard templates, when the template is removed, the corresponding structure will be rendered porous. In the second case of the electrochemical dissolution, this usually involves partial dissolution etching of the material, and this of course also gives rise to specific porous network. On the other hand, in the case of porous hybrid materials like metal organic frameworks or coordination polymers, these compounds, they form 3D and 2D networks, where in the pores that are formed, they reside usually solvent molecules. And these solvent molecules, because they are not countercations, they do not charge balance the structure, they can be removed by using different activation protocols. And upon their removal, a porous network, a porous framework, a porous material can be acquired. However, this is not the case in the porous metal halide materials, because as we just mentioned earlier, the organic cations that reside in the cavities cannot be removed without structural collapse. So in this work, we developed a unique, a novel strategy for generating porosity to this versatile family of hybrid semiconductors. We utilized molecular cages, such as the 222 cryptant organic linker, that acted both as structure directing agents and as countercations. Reaction of the 222 cryptant linker, in that specific case we call it DHS, with lead in acidic media, gave rise to the first 2D porous metal halide semiconductor. This is part of the structure, looking down the 110 direction, in plane that is. The structure consists of 2D inorganic layers of lead bromide clusters that are separated and charge balanced by the cryptant linkers. On the right, there is the representation of one inorganic layer and one organic layer. The organic ligands form a hexagonal or arranged in a hexagonal motif, which is templated by the presence, by the protruding lead bromide clusters. So let's have a closer look on the inorganic cluster, on the inorganic part, on the inorganic layer of the structure. This is part of the inorganic layer. This inorganic layer consists of lead bromide clusters, and each cluster consists of 2 lead bromide 7 capped trigonal prisms and 3 lead bromide 8 endecaedra. To the best of our knowledge, this cluster is unprecedented in the metal halide literature, and it's quite different than the common link-twist type of clusters. The inorganic layer consists of phase-sharing inorganic clusters, and this exact connectivity gives rise to some pore cavities in plane in the inorganic layer of 7.6 angstrom in diameter without taking the van der Waals radii into account. The corresponding silicon crystals were placed in water, and powder excess diffraction studies verified that after 1 year in liquid water, there is no structural degradation. The red pattern is the calculated one from the single crystal structure. The black one is the pristine fresh crystals, and the blue one is the pattern of the crystals after 1 year in water. There is no formation of additional peaks, and there is no loss in crystallinity. On the bottom, we recorded the SEM images of the crystals. On the left, it's the fresh crystals, and on the right is the crystals after 6 months in liquid water. The surface of the crystals is intact. Crystals are pristine, and there is no signs of even surface degradation that cannot be recorded with the powder excess diffraction studies. To validate the porosity, we performed gas option studies using water, deuterium oxide, nitrogen, and carbon dioxide gas molecules. Apparently, the material can selectively absorb and desorb reversibly water and deuterium oxide at room temperature, but it's impervious to nitrogen and carbon dioxide. This means that the material is ultra microporous, and based on the X-ray diffraction studies, the cavity of the DHS linker is estimated to be around 4 angstrom without taking the van der Waals radius into account. So with this into account, the cavity would go would be around less than 2 angstrom. Considering the much smaller kinetic diameter of water compared to nitrogen and carbon dioxide, these studies are in perfect agreement of the adsorption of water and deuterium oxide in the cryptant ligands. We've also found that based on the maximum water uptake, this uptake corresponds to 1 water molecule per cryptant ligand, which was further verified by the DFT calculations. In order to shed light in the local structural configuration and identify whether the water and deuterium oxide molecules are indeed adsorbed in the molecular cages, we performed solid-state NMR studies. This is the 1D NMR spectrum of the proton NMR spectrum for the material. This is with black is the pristine, the recorded NMR spectrum of the pristine compound. The 2 proton peaks are not resolved, exhibiting the same spectrum as the free cryptand ligands. But with aging and exposure of the material at 85% relative humidity, we observed that gradually these signals were resolved, giving rise and also at much higher with time, the peak of water was also recorded. So this was not that conclusive. However, we performed deuterium NMR studies where, of course, there is no deuterium protons on the pristine material, but with exposure at 80% relative humidity with time, we managed to record two signals which correspond to the deuterium atoms and the deuterium atoms from the deuterium oxide molecules in the cavity, and also there was an exchange between the deuterium atoms and the protons of the ligand, which also we managed to record this peak here from the deuterium atoms on the tertiary amine. In order to elucidate local interactions in below 5 angstrom, we performed 2D proton-proton NMR studies, where after 50 microsecond time, we were not able to record a signal corresponding to interaction of the different types of protons. However, after 120 microseconds, we record a much better signal where we could clearly observe the interaction at close proximities below 5 angstrom of the protons of water and the protons of the cryptand ligand, which this verified that the water molecules are in very close proximity with the cryptand ligand. DFT studies shed light on the semiconducting properties of the material. This compound is a direct bandgap semiconductor. This is the band structure without any water molecules, and we added 1 water molecule per organic ligand per unit cell, and this is 4 water molecules per 4 organic ligands. This means in that case there is 100% water loading, and you can see that there is minuscule difference in the optical bandgap for full water loading. This is a great demonstration proving that the water inclusion does not affect the optical properties. We also wanted to identify the number of water molecules that can reside into the structure and into the organic cavities. So this is the initial configuration by adding 2 water molecules per organic ligand. And this is the final configuration of the structure after structural relaxation. Apparently, only 1 water molecule can reside in its ligand, whereas the other 2 molecules were expelled from the cavity. And this is in a perfect agreement with the gas option studies, where we found that the uptake correlates closely to 1 water molecule per organic ligand. As I mentioned earlier, the material is a direct bandgap semiconductor. However, in addition to porosity, the material is also a broad light emitter at room temperature. There is a large energy shift corresponding to between the absorption and the emission spectra. We performed variable temperature PL studies, where we observed minuscule differences between both the PL peak position and the full width at half maximum of the peak. Time-resolved PL studies revealed a lifetime of around 3 nanoseconds, which correlates well to other broad light emitters, other broad lead bromide broad light emitters. We wanted, however, to identify whether this emission stems from self-trap excitons or permanent defects. And for that reason, we performed variable power PL studies. And as you can see, with increasing the power, the laser power intensity, the emission saturates at higher power flux. This means that the emission stems from permanent traps and not self-trap excitons, because the number of tracks are finite, and by increasing the power density, the traps are filled, and therefore they cannot contribute further, increasing the emission intensity. And for the record, this is one of the very rare cases where the broad light emission in this class of materials is ascribed to permanent defects and not self-trap excitons. In order to evaluate whether the optical properties deteriorate upon water adsorption or water treatment, we recorded the PLE, the photoluminescence excitation spectra, for the pristine material and the water-treated one. And apparently there is no difference both in the PL peak position and the PL bandwidth after 6 months in liquid water, which this is a clear demonstration that porosity not only rendered the material porous, but also it didn't affect the optical properties. And the optical properties were maintained even after 6 months in liquid water. Summarizing, we report here the synthesis of the first porous and water-stable 2D metal halide semiconductor. The material exhibits a record water stability for a hybrid material of more than a year. Importantly, the optical properties are maintained after water treatment, at least for 6 months in water. Of course, this sets the foundation for the generation of a new family of semiconductors with tunable porosity and optical properties. As you can imagine, by means of molecular engineering, the porosity can be finely tuned. And this allows this unique new family of materials to be utilized in application beyond photovoltaics and LEDs, such as solid-state batteries, sensing, and photocatalysis. Finally, I would like to, of course, my students are responsible for all these beautiful new materials. And of course, I would like to acknowledge our collaborators internationally, the University of Bath, University of Lille, Yale University, and University of Crete, for their expertise in different types of characterization methods, funding from ACSPRF, and of course, all of you for your attention. And I'm happy to answer any questions. Thank you.